Right. So at the end of the day, so the algorithm works, you alternate these two reflections. The reflection, the unitary use of f, and the reflection about the initial state size 0. You do those back and forth, which overall gives you a rotation. And then you, at some point, you have to make this a classical thing. So what you do is you measure the index. So you measure the index in the computational basis. It gives you some index j. It could be the j star that you're looking for, or it could be just like ket 1, right? It could be something else because you got unlucky. And so instead of outputting the wrong answer, it's a good idea to evaluate f classically on that output. Double check that it's the right answer, and then if it evaluates to 1, then you output it. If it evaluates to 0, you either say I failed, or you re-enter the loop and try again. I mean, you can make it as, you can adjust the parameters to make it as small as you want. Yeah. Right. So we guess k equals n, and k equals n over 2, k equals n over 4, etc. So the running time goes like, I'll ignore the thetas. Square root of n over n, square root of n over n over 2, etc. So that's like 1, that's like square root of 2, that's like square root of 4. And so eventually, until you hit something, until you find something, so if you stop at like k star, then so square root of n over k star, and so that gives you, yeah. So here, if you add up the running times, it's 1 plus square root of 2 plus square root of 4 plus square root of 8 plus plus square root of n over k star is where we stopped. But that's a geometric series where the ratio is square root of 2. And so any geometric series is dominated by the last term up to constants. So the complexity is going to be theta of square root of n divided by the number of solutions. So you don't have to know the number of solutions. That's all I'm saying. It still runs in the same time, up to constants.
If we follow this algorithm, then what if k is equal to, say, between n and n over 2, somewhere like between n?
Yeah, exactly. I mean, yeah. So here, 2 isn't anything special. You can choose different ratios and it'll still work, as long as it's a constant. And the reason, and it doesn't matter if the actual value of k star lies somewhere between them, because the same thing here. Like when you rotate, you don't have to end exactly at j star. You just have to end between angle pi over 4 plus or minus pi over 4 of j star. And so if you're off by, if your value of k is off by a little bit, you'll rotate it too far, or you'll rotate it too little. It won't be a big deal. I mean, that's intuition, but it's pretty clear you can make that work.